Hi dear students, in this section we discuss the electrostatic boundary conditions, that is the boundary conditions for electric field and the electric potential V. What is meant by the boundary conditions? That I will explain here. If there is an electric field that is coming from the source of charges, maybe here you may have some positive charge sheet or something else, and this electric field is traveling through the air or the free space, and on the way it meets a charged sheet. Charged sheet means this contains surface charge density sigma. Then if you know the boundary conditions, that is, this is a boundary that separates this medium, that is medium 1, and the medium above this charged sheet, that is medium 2. Or if this medium is a vacuum and the second medium may also be a vacuum, that are also possible. In this session we consider that on the passage of the electric field there is a boundary. That boundary is a charged sheet. Then if you know the boundary condition, you can predict what is the electric field in this second medium. You know already the value of the electric field in the medium 1, and if you apply the boundary conditions, you can predict what will be the value of the electric field in this second medium. That is, shortly we can say the boundary conditions are helpful in determining the field on one side of the boundary if the field on the other side is known. Fine, let me note down. That is, the boundary conditions are helpful in determining the field on one side of the boundary if the field on the other side is known. Fine. Now let us consider this is a charged sheet and the charge density is sigma and the total charge on the sheet is Q, capital Q. Consider an electric field is traveling from the bottom of the sheet, that is, this is a region 1, and it is going to the region 2. This is the electric field down. This is the electric field up. Fine. Now we have to see what will be the electric field in the upper region, that is the value of this electric field that we need to find out. We know the value of the electric field in the down region. The value of the electric field in the down region, that is a E down, that is a known factor, and we need to calculate, or we have to predict, what is the value of the electric field after passing through this charged sheet. That is, the sheet is this is the boundary. That is, we need to calculate the value of the electric field in the second medium, that is E up. This is possible if you know the boundary conditions. Fine. Now, to derive the boundary conditions for the electric field, we have to resolve this electric field E down and also the E up into 2. That is, here I will split this electric field, that is into two components. If this is the E down, the electric field component along the tangential to the boundary, that is E parallel down, electric field perpendicular to the boundary, that is this is the E perpendicular down. Fine. Now similarly for the electric field the upper side, that I will resolve in the same way. If this is a electric field upper, then the tangential component of the electric field, that will be along the x-axis. Let us write this is a E parallel up, and the electric field, the perpendicular component of the electric field, this is represented by E perpendicular up. That is, simply I have resolved these two electric field into two components. That only I did here. Okay, fine. Now we are calculating the difference in the electric field E when the boundary of the charged sheet is crossed. That is, when this electric field crosses this boundary, we will calculate what is the difference in the electric field. That is the difference in the electric field when the boundary of the charged sheet is crossed. That is denoted by delta E. That is the difference in the electric field. Means here we have the E down and here we have the E up. The difference in these two, that is represented by delta E. Let us write E up minus E down. That is, if you look at this figure, here we have splitted the E up into two components, this E parallel up and E perpendicular up. Similarly, E down, here we have split it into two, that is, we resolved into E perpendicular component and E parallel component. Therefore, this can be written as E perpendicular up plus E parallel up, that is components of the E up, minus this minus E down also has two components, that is E perpendicular down plus E parallel down. Fine. Here I write the perpendicular component together, that is E up and E down perpendicular. This will be E perpendicular up minus E perpendicular down bracket, then plus this E parallel up minus E parallel down. Let me put this is equation number 1. That is, while calculating the difference in the electric field, we obtain these values. Now we have to calculate individually what is this value and what is this value. Then we have to substitute into this expression 1. For this, first we calculate the E perpendicular up minus E perpendicular down. That is our task, first task. That is, if you look at this picture, that is this picture, in this picture, this is the charged sheet and if we consider that charged sheet, that is the electric field due to a charged sheet, if its unit, if its vector is n, that the vector n is a unit vector perpendicular to the plane of the surface, and if this is a positively charged sheet and the charge density is sigma, then the electric field will also be around the same direction in the upper side. Therefore, this is the E up. That electric field is given by sigma divided by 2 epsilon 0 n cap. That's to be denoted as a E perpendicular up. And what about the E perpendicular down? E perpendicular down means from the same positive charge, the electric field will be in the negative direction, and this will be the E perpendicular down. Okay, this is can be denoted by E up perpendicular. This is E down perpendicular, and the area, that area vector is perpendicular to the plane of the surface is n cap, but it is minus n cap. Therefore, here this E perpendicular up, I can write E perpendicular up is equal to sigma divided by 2 epsilon 0 n cap, and E perpendicular down, that can be written as sigma divided by 2 epsilon 0 minus n cap. Therefore, E perpendicular up minus E perpendicular down can be written as sigma divided by 2 epsilon 0 n cap minus sigma divided by 2 epsilon 0 minus n cap. Or I can write E perpendicular up minus E perpendicular down, that is equal to sigma divided by here this will become plus, this minus will be, this term will be plus, then half sigma by epsilon 0 means sigma divided by epsilon 0 n cap. Okay. This is the value of this E perpendicular up minus E perpendicular down. I would like to write this expression in another way. That is, we have used that representation that E perpendicular up, then E perpendicular was the normal component of the electric field perpendicular to the boundary. The same expression can be written in this way. E normal 1 means if this is a charged sheet and our electric field is traveling from the region 1, if I denote this is a medium 1 and this is medium 2, and in medium 2 the electric field is represented by E2, then the normal component of the electric field is represented by here En1 in the medium 1, and the E perpendicular down means you can use the normal component in the second medium, that is En2. That is equal to, in this way also you can represent, that is equal to sigma divided by epsilon 0 n cap. What is the meaning of this expression? That is, if the electric field in the medium 1 having certain magnitude, if it has the same magnitude in the medium 2, then we can write En1 is equal to En2. That is, the electric field in the two medium is continuous because both are the same values. You will obtain this value if En1 minus En2 is equal to 0. That is, the right hand side of the equation should be 0. Then you can write in this way. That is, the normal component of the electric field is continuous at the boundary. But these expressions, the right hand side of this expression is not 0. Therefore, I cannot write in this way. That is, the non-zero value of the RHS of these two equations suggests that the normal component of the electric field is discontinuous at the boundary by an amount this sigma by epsilon 0. That is the physical meaning of this expression. This normal component of electric field is discontinuous at the boundary by an amount sigma by epsilon 0. That is the physical meaning of this expression. To get more idea about this boundary condition, then we will consider an example. That is, we will consider a charged spherical shell. Charged spherical shell means this is a charged spherical shell where all the charges are on the surface. The electric field inside the charged spherical shell is 0, and the electric field at the surface of the charged spherical shell, that is E surface, is equal to, if Q is the total charge on the surface, then it will be Q divided by 4 pi epsilon 0 r square r cap. That is, here this sphere has a radius r and total charge Q. Fine. Then sigma is equal to Q by A, where sigma is the surface charge density, Q is the total charge, A is the area of the spherical shell, that is 4 pi r square. This Q can be written as sigma into 4 pi r square. If I substitute this Q here, then E surface can be written as sigma 4 pi r square divided by 4 pi epsilon 0 r square r cap. Here this 4 pi r square got cancelled. E surface, that will be equal to sigma divided by epsilon 0 r cap. Actually, what is our intention? Our intention is to check whether this boundary condition that we have derived is correct or not. That is, both are the same boundary condition. Then if you write the boundary condition for this particular case, that is the charged spherical shell, how we will write? Actually, here we have the electric field. The electric field of the charge may travel from this to this region, because if this is positively charged, and here we have the electric field on the surface, that is E perpendicular up, or this is we can say E n1, and the electric field in the medium 2, that is, this is E perpendicular down, that is nothing but this E inside, or this we can also represent is equal to En2, En2, normal component of the electric field in the medium 2, because the electric field will be always normal to the surface. Then the boundary condition, that is, we have written E perpendicular up minus E perpendicular down. Instead of that, I can write E surface instead of E perpendicular up, and E perpendicular down instead of E perpendicular down, I can write E inside. Fine. That is E surface minus E inside. What is the value of E surface that we have here? Substitute that value, sigma divided by epsilon 0 r cap minus E inside. Just now we have seen that this value 0, that is sigma divided by epsilon 0 r cap. That is E surface minus E inside that is equal to sigma divided by epsilon 0 r cap. See, we have really proved that is the perpendicular component of the electric field that is always discontinuous at the boundary. That we have proved in the case of this surface charged spherical shell. Fine. Now, what is the conclusion? Conclusion is this one. The normal component of the electric field is always discontinuous at the boundary if there is a charge density, free charges on the surface. If the charge density is 0, that is this 0, sigma is equal to 0, then this expression will be En1 minus En2 is equal to 0, where the electric field will be continuous at the boundary. Okay, but here situation is not that one. There is a charge density on the surface, therefore the electric field is discontinuous. Okay, so far we have calculated this value only in the expression 1. Next we have to calculate E parallel up minus E perpendicular down, E parallel down. E parallel up minus E parallel down. We need to calculate the value of this one. Okay, for this our charge sheet contains surface charge sigma. Then if I take a small path that separate the two media, that is I will take, this is a P Q R S. This is the boundary that separate the two media. Then our electric field that was traveling from this medium to and passes to the second medium. This was our E up, this was our E down. Then we resolved that E up and E down into 2. That is, for the convenience, once again I will write here E up. This is E up parallel to the surface, parallel to the boundary, and this is E perpendicular up and below the boundary, that is here this is E down. Parallel component is E parallel down. This is E perpendicular down. Then to calculate the E parallel up minus E parallel down, that is this equation, we consider this loop, that is the loop PQRS, and we use this expression, that is closed path PQRS E dot dl, because that is equal to 0. That is, if we calculate this closed path line integral E dot dl, we have first the path PQ, this path, that is the integral we have to split into integral P to Q E dot dl plus integral Q to R E dot dl, that is this one, then R to S, then P to S, plus integral RS E dl plus integral SP E dot dl is equal to 0. Then if you check this figure, that is along this path, that is PQ, the electric field line that is parallel to the path PQ, that is our E parallel, because E parallel up in the upper side, because the PQ region is lies in the upper side region. Therefore, the parallel component of the electric field, or the electric field parallel to the length element PQ, is E parallel up. E parallel up, and our PQ length element are along the same direction. The angle between them is theta is equal to 0 degree. Therefore, this I can write integral PQ E parallel up dl cos 0 plus, what about QR? Here, the path that we have considered is very short one, and if the width of the path that approaches to 0, because the path we have considered whose width is very small, that approaches to 0. Therefore, this QR and PS both goes to 0. Therefore, this expression is QR 0, and also this will goes to 0. The remaining term we have RS. The RS means, if you look into this picture here, this RS is towards the left, and if you take the component of the electric field, that is the SR region, the SR region is in the down side, where the electric field line either parallel or anti-parallel to the SR region, that is E parallel down. That is, if you look at here, E parallel down is along this direction, and our SR is along this direction. The angle between these two is theta is equal to 180 degree, where the E perpendicular down component is perpendicular to the length element. The angle is 90. Therefore, this E perpendicular down component do not contribute any magnetic field, any electric field. Therefore, we can write that is this RS component, that is integration R to S, the component of E parallel to the length element or anti-parallel to length element, that is E perpendicular down dl cos 180, that is equal to 0. If you do the integration, that is here one term will arises, that is integration P to Q dl, and in the second term this will be integration RS to S dl. The length element of the closed path that we are considering, PQ and RS, that is, if you look back to this picture, this PQ have the same length as that of the RS. Therefore, we can, during the integration, that we can take it outside, that is PQ will be equal to RS. Finally, we are left with E parallel up minus E parallel down, that is equal to 0. That is, this equation give you E parallel up, and this equation will give E parallel down. Sorry, here I committed a mistake. That is E perpendicular down, this should not come into the picture, because this E perpendicular down means this E, if it is a E perpendicular down, then E perpendicular down will be here, and our length element, that is RS, will be along this direction. This angle will be 90. Therefore, this E perpendicular component do not contribute an electric field. Therefore, this should be E parallel. If you check here, that here this E parallel only contribute. Therefore, this should be E parallel down. Fine. Therefore, this should be E parallel down. This is the another electrostatic boundary condition, that is the parallel component of the electric field is continuous at the boundary. This parallel component can also be written as tangential component, that is E tangential 1, it is a medium 1, the upper side we represent as the medium 1, it will be the tangential one, and the downside if we represent is a medium 2, then where the parallel component means that is tangential component, we can write Et1 minus Et2 is equal to 0. This is the second boundary condition, whose physical meaning is this one: the tangential component of electric field is continuous at the boundary. Fine, or we can write this is as a Et1 is equal to Et2. Both are the stereo representation have the same meaning. While traveling an electric field from the medium 1 to medium 2 in this figure, then where the normal component of the electric field will be discontinuous, the tangential component of the electric field transmit into the second medium without any loss, though there is a charge density sigma on the boundary separating the two media. Fine, that is the physical meaning of this expression. Now if you look back, that is E parallel up minus E perpendicular down be equal to value 0, we have to substitute this value 0 into this expression, the second term in the equation 1. This will be 0. Therefore, let us write what is the difference in the electric field when the boundary of the charge sheet is crossed. That is, we have to substitute, that is E perpendicular minus E perpendicular down. That we obtained sigma divided by epsilon 0 n. Therefore, I can write equation 1, that is the difference in electric field when it crosses the charge sheet, that is E up minus E down, that was equal to E perpendicular up minus E perpendicular down. We have already written in the equation 1. This is E parallel up minus E parallel down, that is here we have the result to substitute, that is sigma epsilon 0 into n cap, here the 0, that is finally we can write E up minus E down, that is equal to sigma divided by epsilon 0 n cap, which means the electric field is discontinuous through a charged boundary along the direction perpendicular to the boundary. Fine. Now let us go to the next topic. That is, so far we were talking about the boundary conditions of the electric field. Next our task is to derive the boundary conditions for the electric potential. The boundary condition for the electric potential V, and this is our charge sheet, and here we represent V up, V down, that is a potential below the charge sheet, and V up is a potential above charge sheet. Then V up minus V down, that is, to calculate the electric potential, we have the relation V is equal to minus integration E dot dr or E dot dl. Then we have to evaluate this integral. For this, we have to construct a closed path, that we take the same closed path that we have taken earlier, is PQRS. But calculate the electric potential V down, what limit we will apply? electric potential varies abruptly perpendicular to the surface. That is, since the variation is normal to the surface, for the electric field we have to take the integration from P to S E dot dl minus, that is the normal, the abrupt change in the electric potential will be along the direction perpendicular to the surface. That is why we are taking the PS, and another integration, that is QR E dot dl. We have already assumed that the width of this path is PQ, that is equal to QR, that is very small, that is approaches to 0. That is, if you write, this is the thickness of the path, that is approaches to 0. Therefore, the right hand side of this equation will be 0. Fine. Therefore, I can write V up minus V down equal to 0, or V up is equal to V down. This is the boundary condition for the electric potential. The physical meaning is this one: potential is continuous across any boundary. We can prove this boundary condition using an example. That is, consider a potential on the surface of a charged spherical shell. That is, this is a spherical shell and it consists of positive charges, where Q is the total charge and R is the radius. Then here V up and V down means, V up means the potential on the surface, V down means potential inside the spherical shell. We know the electric potential on the surface of a spherical shell. That is, if the charge is Q, that will be Q divided by 4 pi epsilon 0 R, and V inside, that is equal to same electric potential on the charged spherical shell at the surface and the inside will have the same value. The electric potential on the surface of the spherical shell is equal to the electric potential inside the spherical shell. That is, V inside is equal to have the same expression, 4 pi epsilon 0 capital R. Is, we know the boundary condition V surface minus V inside, that is equal to 0. That is, V surface is equal to V inside. See, we have the V surface, V inside, the same relation. Therefore, this boundary condition that we have derived for the electric potential, this is exactly true. Then here, what conclusion we can write? Potential is continuous through the surface of the charged spherical shell. Now let us discuss the next topic, that is the discontinuity of gradient of potential. That is, here we will see that the gradient of the potential is discontinuous. Okay. Just now we have seen the previous discussion, that is potential is continuous, but its gradient is discontinuous. That we will prove here. For this, we use this tool, that is, we have the boundary conditions E up minus E down, that is equal to sigma divided by epsilon 0 n cap. Here I will use electric field is equal to minus del V. This connects the electric field, which is the gradient of the potential, and E up I represent minus del V up, and E down I represent minus del V down. Then if you substitute these values into this expression, then E up I can write minus del V up minus, once again, minus del V down is equal to sigma divided by epsilon 0 n cap. That is minus del V up, this will be plus del V down, that is equal to sigma divided by epsilon 0 n cap. If I multiply with a minus sign, then I will get del V up minus del V down is equal to minus sigma divided by epsilon 0 n cap. Fine, this is the proof that gradient of the potential is discontinuous. This discontinuity is always normal to the charged boundary. That is, if you see this n cap, that suggests that this discontinuity is always normal to the charged boundary. Therefore, it is just sufficient to take the normal component of the gradient. Okay, let me note down here. Okay, as I mentioned, as the discontinuity is always normal to the charged boundary, it is just sufficient to take the normal component of the gradient. What is the normal component of this gradient? That is this one. I will write this as a normal component, dou V up by dou n cap minus dou V down by dou n cap. This is nothing but up is equal to, right hand side we have minus sigma divided by epsilon 0 n cap. Then this n cap cancelled. You can write dou V up by dou n minus dou V down by dou n, that is equal to minus sigma divided by epsilon 0. If we collect all the boundary conditions of the electric field and electric potential, then we can summarize, that is E up minus E down, that is equal to sigma divided by epsilon 0 n cap, V up minus V down, that is equal to 0. This electric field is discontinuous, whereas its electric potential is continuous. That is the meaning. Then the gradient of the electric potential, that is discontinuous, del V down is equal to sigma divided by epsilon 0 n cap with a minus sign. And the last one that we have finally derived, dou V up by dou n minus dou V down by dou n is equal to minus sigma divided by epsilon 0. This is the boundary conditions of E and V.
Next we discuss electrostatic
That is
pressure.
the force exerted by the electric field on the surface of the conductor. That force per area is the electrostatic pressure. Now let us consider a conductor, and there is a surface charge density sigma on the conductor. Because of the surface charge, there will be an electric field. That electric field line, electric field is given by, represented by this one. that electric field E is equal to sigma divided by epsilon 0 n cap. Inside the conductor, the electric field E is equal to 0. Okay. Now, from the boundary condition, we know that E up minus E down is equal to sigma divided by epsilon 0. Or E up means here the upper side, that is represented by E surface, minus E down means E inside, that is equal to sigma divided by epsilon 0 n cap. Here there should be n cap should be there. We know that inside the electric field is 0 inside the conductor. Therefore, E surface sigma divided by epsilon 0 n cap. That is, the electric field through the surface of the conductor is this E surface. Fine. Now, if I consider that if Q is the total charge residing on the surface of the conductor, ഈ സർഫേസിൻ്റെ ഈ കണ്ടക്ടറിൻ്റെ സർഫേസിൽ ഒരു ക്യൂ എന്ന് പറയുന്ന ടോട്ടൽ ചാർജ് ഉണ്ട് എന്ന് വിചാരിക്കുക. Then we have to calculate the force on the conductor because of these charges residing on the surface. That is, if Q is the total charge residing on the surface of the conductor, then the force on the conductor, that force we can write F is equal to Q into E. This F is I write this is a average force, and electric field is a average electric field. This electric field is a electric field on the surface only. That is, here E surface is equal to average field outside and inside the conductor. Find this. If it is an average, usually we take E out plus E in by 2. ഇങ്ങനെയുള്ള നമ്മൾ ആവറേജ് കാണാം. E in നമ്മളെപ്പോഴും നമ്മൾ മനസ്സിലാക്കിയിട്ടുണ്ട് E in is 0. E out we have already obtained a relation, that is sigma divided by epsilon 0 n cap. And if you substitute here, this will be sigma divided by epsilon 0 n cap plus 0 divided by 2. This will be sigma divided by 2 epsilon 0 n cap. Then the force F, that is equal to Q into E surface means sigma divided by 2 epsilon 0. If A is the area of the conductor and Q is the total charge on the conductor, then sigma is equal to Q by A is the surface charge density. From this I can write Q is equal to sigma A. Therefore, this Q can be replaced by sigma A into sigma divided by 2 epsilon 0. That is, this F can be written as sigma square A divided by 2 epsilon 0 In the beginning, I mentioned that the pressure is nothing but force per area. Therefore, if I bring this A to the left, F by A is equal to sigma square divided by 2 epsilon 0, where this force per area, this is a force per unit area of the surface of the conductor. That is, this force per unit area, that is nothing but pressure, P can be written as sigma square divided by 2 epsilon 0, and if I want to write this pressure in terms of the electric field, just now we have seen that E outside we have electric field E. If I take the modulus, so if I am interested in magnitude only, this will be sigma divided by epsilon 0. Then this P can be written as sigma square divided by, I write this as epsilon 0 square. Here I multiply it by epsilon 0 divided by 2. If you multiply, you will get the same result. This can be written as sigma divided by epsilon 0 square, that is E out square. This will be E square into epsilon 0 by 2, that is P. Fine. Finally, we can write the electrostatic pressure. P can be written as epsilon 0 by 2 E square. This is the expression for the electrostatic pressure on the surface of the conductor. If an electromagnetic wave comes, this electromagnetic wave consists of both the electric and the magnetic field. Since it contains an electric field, for example, the electromagnetic wave is light, it falls on a surface or on our body or on our hand. Then this electric field on this electromagnetic wave exerts some pressure on this body. That pressure is given by this expression. That is, electric field can exert some pressure on the surface of any body. Okay, thank you very much.